In this video, I will give you some extra help if you need help completing the lesson, Matter is Made of Particles. Before we get started, please make sure that you've read the learning targets and gone through today's learning schedule. You also should have clicked here and opened YouTube to watch the introduction video for today's assignment. When you're done doing those things, come back to the video. Okay, so on page 2, it starts with engage. It asks us to watch a 1-minute slow motion video about a popping water balloon. I'm going to click and open. What are you noticing? I'm noticing the water starting to move out. So at first it was all together and now the water is moving away. But I'm noticing that it's kind of staying together in these water drops as it moves away. And all of this is really staying together. I would expect it to be going all over the place, but the water is actually staying in the shape of the balloon. And it's still staying in that shape of the balloon. So we've got a few droplets going this way, but in general, the water is staying in the shape of the balloon. Wow, it's moving very slow motion. Okay, so now that we've watched that video, we can go back to the lesson. What do you notice about the water after the balloon was popped? What questions do you have? Well, I might delete this and say something like, I noticed that after the balloon was popped, the water all stayed together. Some of it went away, but mostly the water stayed in the shape of the balloon. One question I have is, why did the water stay in the shape of the balloon? When you're done writing what you've noticed, that the water stayed in the shape of the balloon, and a question that you have, let's go to the next part. Remember, you can pause this video if you need more time. Time for Explore. First, it asks us to try these activities. Use the videos and pictures if you don't have the materials. The materials are water, wax paper, a toothpick, an eyedropper, or a spray bottle. I don't have those materials, so I'll just use the videos and pictures. Activity 1, making a drop of water. Fill the dropper or container with water and squeeze the water out very slowly to make one drop on the end. If you don't have the materials, look at the pictures. That's what I'm doing. What happens to the water when you squeeze it out of the eyedropper? Well, I'm noticing that the water drops stuck together, just like the balloon. Up here, when the balloon popped, the water still stayed in the shape of the balloon. And here, when the water comes out, it's still staying together. It's not going all over the place. So that's what I write. The water drops stuck together. Activity 2. How do water drops move? Put 4 to 5 drops of water on your wax paper to make one medium-sized dot like they did here. Tilt the paper to see what happens to the drop and slowly drag your toothpick through the water drop and around the paper. If you don't have the materials, watch this 14-second video. That's what I'm going to do. All right, let's see what happens.
Ready. It's like a train.
Wow, it's all moving together, right? Notice how it's not splitting apart, but it all moves together? Look at that. Very cool. Okay, so I would write here, when I tried to move the water drop around, it mostly stuck together. That was pretty cool. Activity 3, splitting and uniting. That means putting together water drops. Take a toothpick and try and use it to split the water drop apart. And when you have 2 separate drops, use the toothpick to make the drops touch. If you don't have the materials, skip this question. So we're going to skip this question, but I know because I've done this before that if you try and split up a water drop with a toothpick, it's actually pretty hard. They really want to stay together in one big drop. Activity 4, food moving through water. Watch this video of food coloring moving through water. All right, let's watch. Wow, it's really moving all over the place, huh? Interesting. I would think it would go straight down or in a pattern, but it kind of seems to be going all over the place here. All right, let's go back and answer our question. What do we notice about the patterns the food coloring made? Well, I noticed that the food coloring is going all over the place. It's not really following a pattern at all. And all the drops made different patterns. So that's what I would write here. Okay, time for our explain. We're going to watch a video or read an article to learn. Let's watch the video.
Matter is defined as anything that has mass and takes up space. That definition includes everything that you interact with in your daily life, from your clothes, to your food, to your electronics, and everything in between. All matter is made of particles. Particles are the pieces of matter that are stuck together to make a larger object. All matter is made of groups of very small particles. You might notice that the word part is inside of particles. This is because particles are parts of matter. In your activities today, you learned 2 important things about particles. 1, particles of the same kind are attracted to each other. By same kind, we mean like 2 water molecules, 2 water particles, or 2 wax paper particles. By attracted, we mean like they want to come together. 2 particles that are the same, example, 2 water particles, are attracted to each other. In other words, they will want to stay together and not move apart. Some particles of different kinds are attracted as well. You saw the attraction of particles to each other or to other kinds of particles in the activities above. You should have seen that you could get a pretty big drop of water to stick together on the end of an eyedropper or a spray bottle nozzle. The drops also stuck together on the wax paper, but they did not stick to the wax paper. This is because water particles stick to each other much better than they will stick to wax particles. These are the same kind, water particles, and these are the same kind. The second thing you should have learned about particles. Particles move randomly. That means they don't have a pattern. Think about when you saw the food coloring particles moving through the water particles. Once the food coloring was in the container, it moved around wildly, and each drop made a different pattern as it was spreading out. The water was not moving around in the cup before the food coloring was dropped in, and then the food coloring continued to move a long time after it was dropped in. Then, the only thing making the food coloring move was the movement of the water particles. This shows that the movement of water particles in the cup was random. It did not follow any pattern. It pushed on the food coloring different ways at different places. The picture to the right shows how the particles in the water cup might look like if you could see them. Each of these blue dots is a particle. The curved lines are showing the direction and how fast the particles are moving. These are moving this way, this way, this way, this way, this way. The more lines, the faster a particle is moving. You can see that the lines are on different sides of the particles. This is to show that the movement is random. To answer the questions, what are particles? Well, we learned that particles are the small parts of matter. Next question. What did you learn today about particles and attraction? What examples of this did you see in the labs? Well, we learned that particles of the same kind, like two water particles or two wax paper particles, are attracted to each other. They want to stay together. So we learned that particles of the same kind are attracted to each other. The examples that we saw of this were the water drops from the eyedropper and the water staying together, or water particles staying together on the wax paper. Last question. What did you learn today about how particles move? What examples of this did you see in the labs? Well, we learned that particles move randomly. That means they do not have a pattern. The example that we saw was the food coloring moving through the water. I hope this was helpful. You should walk out of today feeling like you understand that particles are tiny parts of matter, that they are attracted to each other, just like the water droplets wanted to stay together, and that they move randomly.
Okay, so now we're done with that. Hopefully you were able to fill out the questions. If you didn't, stop this video now. Now it's time for elaborate. Have you ever heard of antimatter? Antimatter is in a lot of science fiction books and movies. Watch this video to learn about what antimatter is. And then we're going to write at least one question we have about antimatter.
Even if you're not a science fiction fan, you can't help but hear about all sorts of cool kinds of imaginary gadgets, from lightsabers to time travel. However, the reality is that almost everything you see in science fiction movies is, scientifically speaking, actually really pretty bogus. They're not real. But I have some good news. There's one physics concept in the pantheon of great science fiction plot devices that is totally real. This physically real thing is antimatter. Antimatter was predicted in the 1920s and discovered shortly thereafter. Since its discovery, scientists have been able to make antiatoms, including antimatter hydrogen and helium. Antimatter is science fact, not fiction. So what are some of the properties of antimatter? You might be surprised that antimatter is governed by the same rules as ordinary matter. There's nothing all that unusual about it. You can make an antimatter world, an antimatter universe, even an antimatter me. Well, look, there's Anti-Me now. Hello, Anti-Me. Hello, me. So how the heck wait, that might not be a good idea. What's the problem? Well, remember what happens when you combine matter and antimatter? Oh, yeah. I see what you mean. So tell them about it. One interesting thing about antimatter is what happens when it combines with matter. That's when things get exciting. You've probably heard Einstein's famous equation E equals mc squared. If you've cared to dig in what it means, you've heard that it means that energy is equivalent to matter and vice versa. And that's true. However, that statement is incomplete. When we convert energy into a particle of matter, we must at the same time create an identical number of particles of antimatter. It's always the same. So what Einstein's equation means is that you can convert energy to matter and antimatter, and you can combine matter and antimatter to make energy. Now let's take another look at Einstein's equation. E stands for energy, m stands for mass, but the c squared term is just a number, actually a very big number. In the usual metric system, it is a 9 followed by 16 zeros. This means a little mass is a lot of energy. We can work out just how much. Suppose we had an antimatter paperclip and touched it to a matter paperclip. Can you help me out, Anti-Me? Sure. We'll take these matter and antimatter paperclips and touch them together. The energy that would be released when these two things are combined is enormous. About 20 times as much energy as it takes to lift the space shuttle into orbit.
Whoa.
That sounds dangerous. I think I'll get out of here. Bye. Good idea. I'll see you later. It's a natural question to ask if antimatter is dangerous. The answer is no, or more accurately, we can't make enough to be dangerous. The easiest way to answer this question is to visit the Fermilab Antiproton Source, the world's most powerful antimatter production facility. This facility made antimatter protons for about 25 years. In fact, we worked very, very hard to make as many antiprotons as possible. So how many antiprotons does 25 years of tireless effort bring us? Well, if you were able to store all the antiprotons ever made and combine them all at once with an equivalent amount of matter, we'd have about enough energy to warm the coffee in this urn from room temperature up to something drinkable. That's just not a lot of energy, and it clinches the argument that mankind's study of antimatter poses no credible danger. However, antimatter does pose one very interesting mystery. We believe that matter and antimatter are created in equal quantities from energy. In the beginning, when the universe was much younger and hotter, the energy available at that time should have created matter and antimatter in equal quantities. Yet today, our universe consists entirely of matter. Why is that? The answer is rather simple. We just don't know. In fact, this question is one of the most important puzzles of fundamental physics of the 21st century. As usual, a mystery of this magnitude results in many physicists working on it. We haven't found the answer, but we will. And when I hear something, I'll be sure to let you know. Hey, me. Yeah? Good job, guy. High five.
Oh, okay. So now I need to answer the question. One question I have about antimatter. Well, one question I have is, why is it that when matter and antimatter touches, a lot of energy is released, like in that explosion we saw? So that's something I'm going to write. Why is it that when matter and antimatter touch, we see a lot of energy? Okay, time to evaluate. Rate yourself from 1 to 4 on how well you understand the learning targets. 1 is I'm confused and need to ask for help. 2 is I'm starting to understand, but I have some questions. 3 is I can do this, but it takes some effort. And 4 is I can do this well enough to teach someone else. Number 1, I can describe that all matter is arranged in particles and see how those particles relate to each other. That makes sense. Yeah, we know what particles are and that they're made up of. We know that particles are that they stick together, that they tend to attract. Okay. And we can explain what we saw in the water labs using the words particle, same particles, attraction, and random movement. So we know that the particles, if they're the same, like 2 water particles, are attracted. They want to stay together, like we saw with the water droplets. And with the food coloring, they move randomly. So if you understand that pretty well, give yourself a 3 to 4. If you're still beginning, that's okay. Give yourself a 1 or a 2. Time to share with your classmates. Go to the post where you found this assignment on Google Classroom. Leave a comment on the post about something you learned or a question that you have. If you need help with commenting on a post, you can watch this video here. After that, you'll want to respond to something that 2 of your classmates said by saying, oh yeah, similar to you, I'm also wondering about this. Or just like you, I also learned this today. If you're not sure how to reply to a post on Google Classroom, watch this video. Do you have any questions? Is there anything that you need to share with your teacher? Anything that's going on? Anything urgent? Please tell them. They want to help you, but they got to know what's going on. And when you're done, don't forget to press turn in Google Classroom. See you next week.